fly-off location. We're going to move on to one of our first responder talks. We have Tom Judge, who is the Executive Director of Life Flight Aviation Services. It's a nonprofit hospital consortium critical care system, serving hospitals, rural and island communities throughout Maine. He has an extensive background in emergency medical services and air medicine. Tom has worked in private, public, and non-governmental sectors, designing and implementing emergency care systems nationally and internationally. He has served as an air medical and EMS subject matter expert for multiple federal and state committees, including the Institute of Medicine, the GAO, the NTSB, and the National EMS Advisory Council and Department of Transportation. He's also given an expert lecture for our teams before, so you're welcome to look for that also on the HeroX website. So it's my pleasure to introduce Tom. He'll also be serving as an expert for all of our sessions tomorrow. So thank you so much, Tom, for being here.
Thank you. I'm not used to standing behind a podium, but we're recording this, so it's we'll need to do that. So I will say up front that I am not an engineer. I'm not an aviator, right? I'm a medical guy. If you need your life saved, I'm the person that does that. But I do and run an air medical system, and obviously EMS is close to my heart. I mean, I've worked for 45 years as a clinician in emergency care. So I want to talk a little bit today about what is EMS and what is it that we need from you. So the work that you're doing is actually incredibly important, and it's incredibly important all over the world, and we really need this work. So I want to give you a context of what that means. So there's kind of three parts to where we start with EMS. And one is this idea of an uncertain moment. When we get up in the morning, we don't plan to have a heart attack. We don't plan to have a car crash. We don't plan to have a stroke. We don't plan to have something awful befall us. But it happens. In the United States, there's about 28 million calls to 911 every year for a medical emergency. So about every 30 or 40 seconds, a medical emergency somewhere in the United States. And indeed, there's 119 distinct three-digit numbers all over the world to summon help in a medical emergency. See, we have this idea that there's an uncertain moment, and the second part of this is really important and where we really need you to think about as you're doing this, right? Because it's a competition, but at the end of the competition, there's actually something that really needs to be useful. And the second part of EMS is a promise. And that's really, I think it's one of the most profound promises in the history of humankind, right? If you call us, we will come. If you call us, we will come. 24 hours a day, 365 days a year, we're going to have to figure that out. And sometimes it's straightforward, and sometimes it's anything but straightforward. But that promise to be there when needed, at the point of need, is really important. And the third piece of this is the geography of time. When you're critically ill or injured, time and distance is as much a part of the disease process as the disease itself, right? So if you're in cardiac arrest, about every 60 seconds before someone does something for you, your chances of not surviving that go up 10%. And so at the end of 10 minutes, you have a very tough time of doing that. So time and distance becomes a really, really important part of this. And sometimes time and distance is not that far because all of a sudden something happened, right? So the time and distance on what would be a normal road, a road that an ambulance could pass or first responder could pass, and all of a sudden the road's impossible, and now time and distance has changed very, very quickly. And that's a lot of part of what this competition that I see is about. So we have differing environments. We have this idea of urban and rural, the idea of confined space that we need to address, vertical rescue for doing things, the extremes of temperature, surfaces of what surfaces you're going to be on that, the diversity of missions, right? This is unscheduled, unplanned, uncertain, undifferentiated. And in all of this, it's a very high consequence environment. So here's London, my friends in London. Couldn't get to be a more congested place in London. The average ambulance in London travels at less than 8 miles an hour with blue lights and sirens, right? London is a very congested place, and the London Air Ambulance puts a helicopter into the middle of Trafalgar Square. You know, there's probably about 400,000 people in Trafalgar Square almost any hour of the day, right? And all of a sudden you put something into a very intense urban environment, but you could easily be like our colleagues in Queensland, Northwest Australia, right? So very rural environment as well. And we need to figure out what are those technologies, what are those ways we're going to answer those particular environments. We need to think about confined space, of where all of a sudden it isn't an easy place to somehow come in and access and then move out of a space. We need to think about vertical rescue. And vertical rescue becomes very challenging, both technically, but it also becomes very challenging logistically. And sometimes it doesn't have to be very high, right? Time and distance doesn't have to be like this. Sometimes time and distance can be like this. But on a 40-foot cliff, with you're really ill, all of a sudden, that becomes really complex, and it takes a lot of time. We have extremes of temperature. Colleagues up in Edmonton, Alberta, you know, in the dead of winter, and we have these surfaces. So surf rescue on the beaches of Australia. So I need to be able to land in that setting, and I need to be able to land in this setting, where I've now got salt water, I've got sand, I've got blowing, all kinds of things. How am I going to do that in these various different kinds of settings? And then we have these changes, right? So we all, you know, certainly all of us in the US looked at North Carolina last year, and all of a sudden there are no roads, and there are no bridges. And what was a very simple extraction from one point to another point is now incredibly complex. Not a lot of distance, but there's a lot of time, because logistics have changed in an instant. And again, that's where I look at the competition, and why we were like, this is so important because of trying to answer that question there. Or in Katrina, when the entire region becomes unavailable to the normal way that we would travel, the normal way that we would respond in an instant. And how do we address those situations? And ultimately, and in the competition, you know, we're not going to use a live person in the competition, but the idea is that there is a person in the vehicle. So the minute you put a person in the vehicle, especially if that vehicle is not piloted, becomes a whole different piece. So the minute there's a person's life that depends on the vehicle itself, everything changes as well, right? So when we fly our helicopters in, they're little hospitals. We have more technology, we have a higher skill set than many of our hospitals in a hospital that comes through the air 165 miles an hour, lands right there, and can take off again. But there's lots of places that we can't do that as well as we need to, and there's places where the time, because we can't put that helicopter on every corner, but when we put a person's life in the middle of that, it becomes very, very high consequence. And logistically, it becomes a lot. So again, when we're thinking of this competition, I look at this and say, it takes us about the standard in rescue. So I've worked search and rescue for many years. The standard in rescue is you have to move someone 1 mile in a litter across uneven ground. The rule of thumb is it takes 20 people. 20 people to move one person 1 mile across uneven ground or out of the woods. Whereas this competition, you could potentially do that in minutes, right? You could potentially do that in minutes. So the logistics, all of a sudden, what you can produce on the idea of saving someone's life can really change. In this, there's also a series of operational risks that we really need to think about. We've talked a little bit about confined space and obstructions. Wires, for us, wires is always a very big challenge. Winds, again, the temperatures of that and how an aircraft's going to work when it's hot and high or distance. I live in Maine. It was 40 degrees when I left the house this morning. We can, in the space of probably a little bit earlier, more like April, March, we can see a 60 to 70 degree temperature in a single flight. A temperature swing of 60 to 70 degrees in a single flight from northern Maine down into southern Maine, on a morning in April. So how the aircraft is going to adapt to that. What's the aircraft's endurance? And when GoAERO came to us and we gathered a bunch of medical people, air medical people from around the country, to help design the competition that you're all going to enter, those challenges, endurance is one of them, right? That this is going to becomes a very big challenge, and people, we're looking at new technologies all the time, but it's like, I need to go out 170 miles, and I need to do that under instrument flight, so I need to have an alternate, and I need to be able to get back. So that endurance becomes a very big challenge. Again, the surfaces issue, night operations, that everything becomes much more complicated, and then visibility. So the complexity of operational risks, as you're developing this and you're developing your safety profiles, you really need to think about, okay, we're going to address these in different ways. So again, when we don't have easy access, clear access into an area, how are we going to adapt to that? The wires that we can't see, especially at night. And wires are a huge, huge issue for any aircraft in the low altitude vertical space that they're doing that. So that the wires, what we're going to do, and even, we look at Europe, and Europe's done a lot on the mountain passes of looking at new technologies, is can we put something on those cables crossing the valleys that could get picked up in LiDAR. So when you're moving across them and you can't see them, is there a way to think about how we would avoid that obstacle? I have to go back to the rules. I don't think we put any wires into wire environments in the rules per se. The winds, and how are the winds going to work in different settings? We do a lot of work in meteorology around the country of building new weather systems, looking at how the FAA is going to adapt to new weather technologies, but looking at microclimates, and especially in urban areas of what's that microclimate, is that the wind shear that we might see coming off the Front Range in the mountains in Colorado, well, it's a different scale, but it's similar to the wind shear that we might see coming off a building on Wall Street in New York. So how are we going to do that, to work in those technical, with those risks? Again, the extremes of temperature and what that surface becomes of how we can get in and get out, and can we do that safely? Can we land something and not have a dynamic rollover, right? So how are we going to do those fine touchdowns, and what's that surface like? And then, or if it's hot and high, right? So, and when the competition, the place isn't announced and what it all kind of looks like, you're going to be some, we always say in medicine, when you hear the thunder of hoofs, think horses, not zebras in medicine, but I'm sure that when the competition comes, you may find a few zebras running through the competition as well. So what are those, how is the aircraft going to react in those very differing conditions for doing stuff? And again, the logistics and the humidity and the weather, what does that look like for an aircraft to do this? And again, this is setting up a rescue of a single person. It's hard to see the litter at the back of the line, but there's a front line and a back of the line, and you keep changing the line to move that litter up an incline. Or again, this is, you know, in Maine, you know, one of our national parks, not high cliffs, but that becomes very, very challenging with the technology we have today, which is we have to get someone there, they need to rappel down, they need to put this person in some sort of litter, and then they need to winch them up. What if we had a completely different way to jump that cliff? So that's why I see these things as so important to us. And then what do we do at night, right? How is this going to be at night, and what is the safety margins that we're going to need to employ at nighttime? And what do we do? You know, this is instrument flight of what do we do when we can't really see. And so now technologies, you know, the new sensors, all of that coming in to play is going to be important, but we're going to have to think about how we do each of those. And finally, I think that as you think about this, and as you know, my plea to all of you, as you develop your, you know, pieces, and I was lucky enough to be one of the judges in the first round, so none of us saw all of them. You saw some of them. Really innovative thinking, a lot of thinking, and there was thinking about, okay, I'm going to win the competition. I'm going to design something that will win the competition, which of course, that's the prize, right? I look at that and say, what I'd really like to see at the end of it is something that works, something that can actually be functional. So when we think about that, we're going to really need to think about what is the reliability. And I think all of these things become the challenge of the competition, right? Because you need to get through the competition. But the reliability, the adaptability of a system. How can we adapt this in sort of a little bit different mission configurations? How precise can this be? And we're there. I mean, our helicopters, 4-axis autopilots, pilot can take them off, they can dial in, it'll take you to exactly where you want to go, 10 feet off the ground. That last 10 feet is still a pilot function right now. So, but as we go, and certainly we look at that and look at these, and I think there's other parts as you're developing these technologies, that's a question. In the United States, virtually every single medical helicopter is flown by a single pilot. If the pilot has a medical emergency, which occasionally they do, not rarely, but occasionally it happens, how does that aircraft get safely back on the ground? Right, so that last 10 feet, those are the kinds of things that you're doing. What are the safety technologies and what are the redundancies of the safety technologies that you're going to put into that aircraft? And I certainly in the first round there was a huge variability around that, and it gets tightened up as you go forward. What is the space, weight, and energy penalties? That's a huge challenge for us. You remember back when, you know, 4 presidents ago now, they decided to have the new presidential helicopter, right? So there's a big competition, and I think at that point Augusta and Boeing won that competition, and they won, here's the new presidential helicopter. And then the U.S. Navy got a hold of it, and by the time the U.S. Navy was finished, the helicopter really couldn't fly anywhere. You know, it's like, we're going to put anti-missile systems in, we're going to do this, we're going to do this, we're going to do this, and all of a sudden, there's lots of weight, and there's lots of space, and there's lots of energy penalties. So as you're designing, I think you really need to think about that in any aircraft, space, weight, and energy is a penalty. Again, the idea of endurance, right? And if you think about Katrina, or you think about North Carolina, it wasn't just one person. It's just we have to keep going this out, again and again and again to do this. What is the operating cost? So again, not part of the competition, but I would, you know, if we're going to have something useful at the end of this, the operating cost is important. The capital cost of a new aircraft for me is is a big nut to crunch, the operating cost is much more important to me. The operating cost and the reliability is actually much, much more important to me on a 10-year piece. So that operating cost versus capital cost and reliability it becomes performance for me. So with that, let me finish. I'm happy to answer questions. When we did the Institute of Medicine report on the emergency care system and the EMS at the crossroads, we described it as corporate company. It's like knowing is just not enough. It's not enough. You actually have to figure out how to get it done. And willing, just being willing is not enough. And that's really the heart of EMS. Knowing's not enough in itself. Willing's not enough in itself. It's rolling up the sleeve. So I think this is an incredibly exciting journey that you're on. As a clinician, I look forward to seeing the results. And I think that you know, and I tell this to people all the time. And we bought some helicopters the last couple rounds ago. And when we finished in the factory, and I was like, get everyone down here on the floor. There's maybe 175 people that have worked on this aircraft. And I said, look, this aircraft's going to fly away tomorrow morning. We've just done all acceptance flights today. It's going to fly away. You're never going to see this aircraft again. You'll know where it is, but it's never going to come back here. But I want to tell you what it's going to do. And I want to tell you what that means to people in Maine, right? And people have sort of never really thought about that. So what you're doing is more than a competition. It's more than something really cool. It's a really noble purpose. And I hope you all understand that and that's part of the motivation for winning the competition is this is an incredibly noble human purpose. So happy to answer any questions about what we're looking for in the vehicle, and I'm certainly looking beyond the competition. Thank you.
Mr. Judge, do you think it's possible for a team to present and possibly even win the competition with an asset that has no real chance of being bought by an association like yours? I mean, is there a significant difference between, as you stated, winning the competition and going into, even a smaller scale company?
I think it's a good question. And when I got my first round of Kings and Judges, and I went to the bosses and said, tell me about this, because I'm looking at this vehicle that is really clearly been designed to meet the competition challenge, to do the 3 tests. At the end of that, I'm not certain that it's going to be useful to anybody without completely redesigning it. So for the competition is the competition. And because I think that the idea is to explore the technologies, explore how the technology can meet those performance requirements in the competition. Personally, I would hope that the teams would all look beyond that and say, what could this do? And and there were certainly teams that had sort of already begun to think about that, right? They went down to their local fire department and said, if we could design something that would do this, would you be interested? And I think those become really important pieces. So the answer is, yes, we can win the competition and not have a vehicle that's commercially developable. I would hope, and it's my plea to all of you as a clinician, right? I'm the person that's trying to figure out how to save people's lives. And sometimes we just run out of tools. And it's hard when we run out of tools. And if we had a better tool, we could do something even greater. So that's my plea to all of you. Other questions?
What's a goal, aspirational, would you say, ops or capital cost that you feel willing to take a risk?
Yeah, so that's a great question. One would be, so the question is, So we designed something and now we're gonna commercialize it. What's that price point? And then, so I said there's two parts to it. So as I'm saying up here, one is there's a price point, right, which is the capital cost. One is the operating cost, and one is the performance cost. So when we did a competition some years ago, you know, RFI, RFP, you know, 3 stages of RFP to buy helicopters, right? So, and lots of people get a vote. The chief financial officers of the healthcare system, they get a vote. The people that got the highest weighted vote were the maintainers. The engineers got the highest weighted vote because I needed to know what they thought of could they keep that aircraft operating every day. So a new helicopter, light twin helicopter, is in the vicinity of $7 to $14 million right now. When you think about how often that gets used and how you spread that across, I think that, and these aren't going to be, I don't see anything coming out of this competition that's a replacement for that helicopter, right? I can go out 170 miles, I can go at IFR, I can pick up, you know, a 300-pound patient, I've got, you know, 600 pounds of medical technology, I've got a crew of 3. We're not going to replace that in this competition. But we're going to get that intermediate stage, right? So I run a big system, but I live in a little tiny fishing town. And I was in the volunteer rescue for 50 years in a little tiny fishing town. We've got 25 islands, not very far. You know, some of them are maybe a hop, skip, you know, I could maybe, if I was really good, skip a rock to them. But it's an island. There's no bridge, right? So it's these kinds of smaller pieces. So then you have to think of like, what's the price point? What's it going to cost to operate it and maintain it? How many times will it get used? So I think that if you're looking at fire trucks right now, and there's a big problem nationally with fire trucks because one of the other industries that's been consolidated is fire trucks. And so the price of fire trucks has gone up about 400% in the last 4 years, and the time to get them. But you're looking at it, so I think when you start thinking about this, and here's my comparable. So that ladder truck now, that rescue ladder truck's going to cost me about $2.5 million, right? So it's going to get used X number of times in a year. When you have it, there's no other replacing it, right? You either have a ladder truck, you don't have a ladder truck, you don't have access. So I think that you're going to see in that sort of range of something that could be commercially viable. So $1 million, $2 million, maybe a bit more, and that's something that functions. Other questions? And then we would look at it for sure.
Sorry, Pete Jr. In terms of liability, what I think I heard you say is, again, we're not looking to replace a helicopter. We're looking for basically, instead of last mile delivery, last mile rescue. Is that a good summation of what you're talking about?
Certainly I see it, I see it that way. Now, are there other people that are reinventing helicopters? And the answer is yes. So when we're working, and we know people who are looking at reinventing a helicopter that can, you know, okay, so now instead of two twin jet engines, I have a jet engine and turbo, and I can make that electric and a hybrid it, and I can do things like with the lift capacity. But I don't see that any of these vehicles has a 7,000, so a light twin for me is a 7,000-pound gross operating weight, right? So 7,000 to 9,000 pound gross operating. I don't see that in this piece. That doesn't mean it doesn't exist. I think there were some people that had some pretty large pieces, but it is this, you know, if you think of these environments that we're trying to get in and out of, those environments have become really difficult, right? You know, so for this young woman who had fallen off that cliff and had, you know, broken about, you know, 7 long bones, lacerated her liver, punctured her lungs, had a closed, head injury. She's running out of time on that cliff. Now, luckily, we got to her, and luckily we got her out of there. But time was not on her side. And that kind of piece to me is incredibly important.
Once she was taken up that hill or whatever you want to call it, what was the next step? Was she moved through that forest area, or was she taken to a helicopter or taken to the ground?
Yeah, what you can't see right behind there is there's a road, so there's a helicopter landing in the road.
Okay.
And so it's a combination of local fire, our people, et cetera. So that kind of piece, that's not very far, and it's not climbing Mount Everest, right? This is 60 feet. But 60 feet can become almost insurmountable for doing it. So lots of those kinds of pieces of how are we going to get in and out of these very complex places, and then how are we going to build the safety systems into the piece so that you're not going to have a wire strike when you come back. Other questions?
Was the reason that cliff scenario you were just showing, was the reason why the helicopter didn't directly go down the cliff because it was just too narrow, not enough space?
Yeah, if you look at the landing surface, we would not be able to land on that. And what you don't see here is this is the ocean.
Is hovering not an option?
Hovering in that case would not be an option. Now, we don't do hoists, right?
I see.
So if we were in a different aircraft, our colleagues out in Salt Lake do have hoists. We don't do hoists, we do critical care medicine. That would be a potential option. But again, the other part of helicopters, and this is important, is that there's not one in every corner, right? So the helicopter is a regional asset, covers a large space. We cover 50,000 square miles with 3 helicopters, right? So it's and hundreds of islands. So not a lot of people, but whereas the fire department could have something this size, right? So it doesn't necessarily need to be us. It becomes a different configuration of the first responders.
So that beach example, you couldn't land there. Is that a common example where a situation you just can't land? Is that a common thing, or like?
So it's interesting. So in we fly an aircraft like this as well, so it's a wheeled aircraft. And over the years, we've had about, probably 4 or 5 times that we couldn't land somewhere, but sometimes we can't land close. Right? So now all of a sudden you're dropping the crew and you're running across the mountaintop to get someone. So being able to land precisely or put it into something, and of course then our the vendor at the time was like, we're not going to land any helicopter in a frozen lake in Maine. Right? There's like 24 inches of ice in those frozen lakes. So we'd get a call for a snowmobiler, and they're like, we're not landing on a frozen lake, so the Army sends a black hawk and they land on the frozen lake. Like, okay. So. Any other questions? Well, I hope this is helpful, and I really, as a clinician, I admire what you're doing, and it's so important to us. And I really look forward to seeing the next round's results. And I would imagine, to your question, I would imagine that there will be multiple commercial applications that come out of this competition in different parts of the world, in different operating environments, and they're all going to make an incredible difference. So good, as we say in Australia, good on you. Good on you.
Thank you.